Very good. Welcome to this lecture in which we continue to study the information entropy as was first devised by Shannon. So what I'm going to do is bring out my full screen, and we're going to talk about the properties of this entropy. We're going to first start by some comments. So here goes comment number 1. Since P is always something that is between 0 and 1, we're talking about discrete probabilities here, then the log of P tends to be negative. It is equal to 0 when P achieves 1, then for 0, it becomes, when P is 0, it becomes minus infinity. So what this means is that the log of P there is always going to be negative. With that negative sign in front, that means that the entropy is always going to be positive. Very good. And it achieves, and it is 0. So, and it's also 0, as P is equal to 0 when the probability happens to be one of these probabilities happens to be equal to 1. So, for example, the jth alternative happens to be 1. Then, in that case, the PI happens to be 1 for one of these terms, in which case the log is 0, and for all the others it's 0, and then 0 times log 0. The idea is that the P dominates over the log of 0, and you always get 0. So this is the first important comment. Entropy is positive. It's also possible to check, and we'll do it in a little while, but for the maximum of entropy, the maximum of S is achieved for the uniform distribution. So this is I equals 1 to n possibilities. And when you do that, the maximum is going to be minus k, the sum of 1 over n, so all the way to n here, the log of 1 over n. Now, none of these terms depends on I. So what we have is n terms, n equal terms, like that. Cancel the n's, cancel the minus sign, and you have that the maximum is equal to k log n. So we have here a basic inequality. Entropies in the discrete case are supposed to go between 0 and k log n. Very good. Next comment. 2. Conceptually, this is going to be one of the most important comments. There is no such thing as the entropy of a system. Now, this is important because if you've taken courses on thermodynamics and statistical mechanics and whatever, we're always talking about the entropy of the system is this, the entropy of the system is that. There is no such thing. For one thing, let me give you the first argument. two different agents with different amounts of probability, with different amounts of information, will assign different probabilities. Therefore, two different agents can assign different entropies to the same system. So, two different agents can assign different probabilities, pi and pi prime, leading to S not being the same as the corresponding S prime. So the entropy, just like the probability, is not a property of the system, it is a property of the knowledge, the information the agent has about the system. Very different animals. To be, here's another way to realize that there is no such thing as the entropy of the system. Suppose that you look at the grouping axiom. Let's write it out again. The entropy, the amount of information that you have to provide or you have to get in order to nail one microstate in one installment. If that information comes in one installment, is SP. If it comes in two installments, then you have the amount of information that has to be provided to nail a group, plus the expected amount of information to single out one particular microstate within one of those groups. Now notice the following. Here you have an entropy. What we want to argue is that there is no such thing as the entropy of the system. Now here we have one system that's being described with two different entropies. This entropy here tends to be a fine-grained description, a description in full glorious detail. That's what it's called, a fine-grained description. While, let me write it again, this guy here is a more coarse-grained description. What this means is that you're describing the same system. Here, you are really trying to figure out what is the amount of missing information to nail one of the microstates. Here, you're trying to figure out what is the missing amount of information to single out one of those groups. Both refer to exactly the same system. The P that appears here is a coarse-grained description. The P that appears there is a fine detailed description. But they both apply to the same system. So in this case, one single agent can have two different descriptions of the same system. And the two descriptions get different entropies. So this is like very crucial. It's not so much what the system is doing. Who cares what the system is doing? It's how you describe it. So in this case, the entropy is a property of the description. In the case 2a, it was a property of the agent state of knowledge. For example, if you're trying to describe a fluid, you may use as your variables the positions of molecules. In that case, you would describe it with an entropy that is of this type. But on the other hand, you could try to describe it in terms of densities or pressures or volumes and how those quantities are varying. And so then you would have a coarse-grained description, and it would be more appropriately described by something like that. So, crucial, there is no such thing as the entropy of the system. Just like there is no such thing as the entropy of the universe. And so there are many misguided uh, formulations that people have out there about entropy, and this is the way you avoid them. Third comment: when we write the entropy as minus k p log p, there is a constant up here, and similarly there is a constant out there. This is taken to be the log base e. The constant is essentially arbitrary. We are mostly going to be concerned with maximizing entropy. So whether you maximize with a k equals 1 or a k some other value, the results are always going to be the same. Maybe I should have it more explicit here. Let me go back here, and I should say, there we go, that the entropy here that we have here is positive, of course, provided that k is positive. Okay, my k being positive. Okay, let's continue. So usually one can choose the constant here being Boltzmann's constant, which is 138 10 to the minus 16 ergs per degree Kelvin. It had to be, if it were dq over t, it has to be an energy divided by a degree, right? So that's how it comes. Another possibility is to choose k equals 1. That's my personal favorite. It makes beta, which is 1 over kt, just 1 over t. And another way to say it is that an energy like kt is just t. In other words, t has units of energy. The units of t in this case are energy. So let me see, this is 3a, this is alternative 3b, and the units of entropy, you see, if with Boltzmann's constant you have energy divided by temperature, the units of entropy, if you choose k equals 1, are going to be just dimensionless. No units. And you can see it from here. P has no units, right? Log P has no units. So this is 1. Entropy has no units. I like that. That's the most elegant way to proceed. Most books stick to having Boltzmann's constant equal to something like this. There are many books that choose k equals 1. Landau and Lifshitz being 1. It's my preferred one. In computer science and information science, and engineers, they like to choose, so for computers and information science, they like to choose k 1 over the log of 2, which is 1.4427 and change. And under those circumstances, the entropy then becomes minus p log 2 of p. And in this case, one says that entropy is measured in units called bits. Very good. So there is a fair amount of freedom in the choice of that k, which amounts to the freedom in the choice of the log. I prefer this. Now we hit a more conceptual one. So far, if you look at what we have here, all of this is fairly uncontroversial. Entropy is between bounds. This formula is between bounds of 0 and k log n. Quite clearly, the entropy depends on probabilities. So depending on what probabilities you use, you're going to get different entropies. The probability is not a property of the system, so there is no such thing as the entropy of the system. And finally, the overall constant is very much up for grabs. What I want to discuss next is the tricky one, which is interpretation. And this is where it gets, I would say, a little bit confusing, and there is a reason for the confusion. Typically, we would say it's something like amount of information. A problem here is that we do not really have a very clear idea of what information itself might be. So how do you measure amount of information and you do not quite know what information is? That's the source of all the problems. So one possibility is that information is defined by this quantity S. Period. You define it like that. Is there anything wrong with that? No. Remember, definitions are never right or wrong. Definitions are useful, more useful, less useful, but they're not wrong. You can define things any way you want. So the question is whether this definition, in which you define amount of information or amount of missing information by giving the entropy, is actually useful. One comment that we might give in this respect is that unfortunately this definition of information does not agree with the colloquial meaning that we have for the word information. Does not agree with the colloquial meaning. Presumably, if I ask you a question and you give me information, you give me an answer, right? I'm going for the colloquial meaning here. I ask you a question, you give me an answer. If this definition is correct, the moment that I acquire information, the entropy should go down. The maximum of entropy is maximum missing information. If you have more information, you lower the entropy. In fact, we saw that is actually pretty good. When you have maximum information and you know precisely which is the alternative I that is true, then the entropy is 0. This supports the idea. You get information, the entropy goes down. But this doesn't quite work very well all the time. It works in that particular case. This does not agree with the colloquial meaning. The example I like is the following. Here we have the probabilities. My keys are always in my pocket. I'm a very careful guy. I always have my keys in my pocket and I know where they are. The probability that describes the location of my keys is very sharply defined. Here is my pocket, right? They're precisely located there. Now I put my hand in my pocket and I acquire information, right? What I find out is that my keys are not in my pocket this time. I look, they're not there. I acquire data, the keys are not in your pocket. I update my probability distribution, and what I end up getting is a probability distribution that says, well, the keys are not in your pocket. They could be essentially anywhere. So this is before, and this is after. So I have acquired information, and the probability becomes very broad, and the entropy has increased. It goes from being 0 to being almost the possible maximum value that it can achieve, which it achieves when you have a uniform distribution. So here you have a serious problem. There are situations in which you acquire information and entropy increases. It's going in the wrong direction. If information were to be defined just by entropy, you would not be able to explain this. So we have a problem. This definition does not agree with the colloquial meaning of the term information. As I said before, nothing wrong with this, except that it is very inconvenient. This is not a good definition. So let's go for another one. When I looked, another interpretation, when we looked at, come on, my tablet is being, here, my tablet is being a little bit finicky today. So when we look at the group in Axiom, we understood this group in Axiom as saying you can provide information about the missing information about which is the alternative that is the true one, all in one step or in two steps. In one step here, in one installment, you decide what is the group, and then in the next step, you give the expected information that's missing for the group. Expected. So could it possibly be that entropy is actually describing expected information? Is S an expected amount of missing information? In principle, it could be, right? Let me see. Look, if it is going to be expected, let's set k equals 1. I have p log p. So quite clearly, s can be written as minus, or let's put it like this, the expected value of the log minus log p, which is 1 over p. So if the entropy is an expected amount of something, is log 1 over pi the amount of info we gain when we find I is true. Okay, unfortunately, it doesn't quite work very well. Let me see. Let me rewrite this other sentence here. Let me polish this. Is log pi the amount of info we gain when we have probability pi and we learn that I is true. This looks promising until you realize the following. Suppose that this is a very, very unlikely situation. You're almost certain that I is not true. Almost the opposite of this, right? Here I was almost certain that I had the keys in my pocket and then I find it's not. Well, suppose that I am almost certain that I is not true and then I find out that I is true. Suppose I'm throwing you letters of the alphabet randomly. You just open a book, put your finger, figure out a letter. Most likely it's going to be the letter E. In English language, that's the most likely letter. It's very unlikely you're going to put your finger and find a Z, right? So your probability of getting a Z is very low. And yet, you put your finger, it's a Z. You got a lot of information. That sounds very good. But there is a problem. And the problem is the following. If pi is very low, this is a very large number. And log pi is a moderately large number. It's a moderately large number. But isn't it true that you would expect that in order to convey a lot of information, you expect to have a rather long message, while just saying it's the letter Z could be conveyed by a very short message. In fact, all you need to do is say, okay, if you receive the message 0, it's the letter Z. If you receive the message 1, it's any other letter. That kind of message will tell you it's Z in 1 bit. So you see that deciding what conveys lots of information or not depends a whole lot in how you have programmed your language. You can have a language that in one symbol you can say something that's extremely unlikely, and in principle that's going to be a lot of information, but the message is like incredibly short. So it doesn't quite work very well either. So one of the things that people do in this case, because after all, if the pi was very low, then this is large. Yeah, you do the math, it's large. One thing that people do is they call this quantity 1 of pi the surprise of I. So this is the surprise of I, and you could say that entropy is the expected surprise. Now that's perfect, but please notice how now I'm not using the word information anymore. I'm using the word surprise. Okay. Here's another interpretation. C. S measures uncertainty. Now that's not too bad. After all, if you have a distribution of probabilities that is very sharp, this has low entropy. And if it's very broad, it has high entropy. So it's sort of like, it's sort of intuitive to say, yeah, S sort of measures uncertainty. But then you say, wait a minute, don't we measure uncertainty with the variance? What's wrong with measuring uncertainty with the variance? Why do we need entropy? Do entropy and variance measure the same thing? Good question. What is wrong with variance? Very good. So you see, what's wrong with variance? The big question is, what is information? And answers go all the way from information is physical to information is this, information is that. Later on in this course, we're going to adopt a definition of information that I find much more compelling because it agrees with our colloquial meaning for the term information. Namely, it's the answer to a question. It's something that helps you change your mind. You learn something, you update probabilities. So this is going to be the big one of the important questions we try to answer in this course. So one of the things I'm doing when I call your attention to all these flaws in the interpretation of the Shannon entropy is that it opens the road to clarifying what entropy might mean and eventually how we end up using it. Jaynes and Shannon eventually gave up on trying to interpret entropy. At the beginning, they were convinced, oh, amount of missing information and all that. Over time, they just sort of gave up. They started to realize the flaws in interpreting entropy, Shannon entropy, as amount of missing information. And so they just said, look, the important thing is the formulas we have, the inequalities we have, the how we use this tool, and that leads to undeniably useful concepts. So let us not worry too much about what information entropy means. Let us learn how to use it in useful ways. I sort of feel their pain, but on the other hand, the way we solve equations is more or less clear and objective and specific. But the way we set up equations depends a whole lot on what the meaning of the various concepts are. So we may learn to use entropy without caring too much about its meaning, but at some point it's going to come back and haunt you. So you have to be careful. Very good. So what I want to do next is I want to discuss a simple case. But that, it's best if we do it in the next half of the lecture. Thank you.